So yes, I will try to give you an overview of several topics that I followed during the years. And I always work with particle detectors. So I will give you multiple examples of it, low energy and high energy particles as well. So LHCb is of course high energy, but I started from something which is more close to medical physics, and then I went to high energy physics after. So I have quite an overview. So I think I can help you understanding where it is, I hope. So okay, so when Angelo asked me to do this, the first thing I did was to Google what R&D in general is, because I mean I had my idea, but it's always good to start from some kind of definition. And I didn't have a definition myself, of course, so I had to find it somehow. And I found, so these are the first three references that I found on Google, which is what I do when I don't know how to define precisely something. And I was not very happy with all of them, by the way. So we can go through them. The first one is of course Wikipedia, which is a first reference for everything. So R&D is the set of innovative activities undertaken by corporations or governments in developing new services or products. And this I didn't like already. And Britannica, which I knew that it was also kind of industry oriented, says that this research and development are intimately related, and it's fine. And by processing both of them, you can have new products once again in a new form, or old brought into being by novel technological development. This okay. This I also didn't reflect what I had in mind for R&D in general. And then I went to Springer, which is a publisher, which also publishes some of our papers. So I thought that I was going more towards what I had in mind. It was the case at the beginning, at least because it starts with a broad category describing the entity of basic research, applied research and development activities. And in general, research and development means systematic activities in order to increase the knowledge and how to use it. And this is very nice. But then it screws up with the rest, because it says and use of this knowledge when developing new products, processes, and services once again, and then it goes through again the same story as before. So it is true that somehow it can go there, and in many cases it does, but it's not the entire story. So if you give a definition of something, it has to be as broad as possible, and this is not. So, okay, I was not satisfied by this, and because it's very market driven in general. So it's and it's not the only thing that R&D does. It is one of the things, and is of course nowadays most of the things are market driven. So this is naturally one example, but it's not the only. So then I thought, what had me thinking about my idea of R&D from the very beginning, because I had it also before the university. So I started to think of what I thought when I had your age, and then of course I went to video games because it's a perfect example of what one can get, which is outside of the internet bubble. There is games, which is something that we always used to learn from the very beginning of when we are kids. So this is one example that a game that I played, and that influenced my idea of what R&D is. I played several of these Civilization series. So therefore, the one that doesn't know, I think many of you know, but for the one that doesn't, you have a tribe, and somehow you have to fight with other tribes to thrive in this world and create your civilization and make it successful. And in the process of doing it, of course, you go through his history, you develop your culture, your method, somehow your civilization, and with that technology comes along. So believe it or not, I think the technology idea that this game gives is better than the definitions that we had before. So in this game, you have some kind of technology tree, so you can by unlocking some features of the technology development, you get many more, and then this cascades, and you have many more that gets available after you unlock one, and so on and so forth. So you start from discovering the wheel, and then you develop pottery mining, and you discover writing, and you have as well, at some point at the very latest stages of the game, you have advanced AI, which is something that you will see probably in the seminar that you will have with other people. And then if you look through it, you get other hints of why technology is developed, and this is basically war, because many of these things along the technology tree, they always mention that somehow you have you can use some of this knowledge to fight other people and other civilizations that are getting along with you in the game. And this is true also nowadays, and it's not mentioned, but it's just the truth. Many countries invest tons of money, and much more than what you think, to develop weapons to kill other civilizations in our nowadays society. And this is true also. Also with this other example, I mean, you see combat strength and so on. But there is another sub definition, or somehow another way of making more general, and this is something which is not covered by the game as well, but somehow it goes through it, and I will come back to it in a moment. But basically, it's me. So it's we have this is a cameo that I made. Of course, I'm not in the game, but if I was to, I was introduced with the patch in 2015, and they cost a lot of money, of course, because I spend a lot of money for materials. Maybe Angelo knows. And I come along with photonics experience, calorimetry, which I'm doing right now, and I'm part of the LHP collaboration, as he said, and I participated to several projects. But to go back to the game, what this one of the way that you can win the game is by exploring exoplanets. And this is astonishing, because it's not something which is covered in the other definition. Is not fighting other civilizations as well. It's just the pure exploration that gives you the win of the game. And this is something very neat, because it's indeed something which I feel very much. Exploration in the work that we do is something that pushes me often. So and I think is the beauty of the R&D work that we do in physics and in other examples, of course, but physics is the one I'm bringing along. So there is no goal there to find. I mean, not for sure, at least, and you have nothing to fight. It's just the bare principle of going somewhere that we were not before, and this is beautiful for me. So this is R&D as well. And so if we have to go back to the interpretation that Springer gave, I would just cut it. So you just take the beginning and you stop the point where it should stop, which is the more general idea of R&D that you can get. So in general, research and development means systematic activities, and systematic is important, because being systematic is, you will find out if you go through, being systematic is the key for the success in the lab. Systematic activities in order to increase knowledge, full stop. And then this knowledge can be used for whatever. I mean, it has to be published. In our case, it can be patented if you want to get money out of it. It can be many other things, but in a more general, in the most general way, this is the definition. Okay, so my specific case, okay, then I can give you also an example of my typical day. Maybe you are interested. It starts all with coffee, because I'm Italian, and coffee is also, it boosts activities a lot. Mail correspondence, because it's necessary. Work in the lab, which is the reason why I do it, basically, together with simulations, which are necessary and very beautiful as well. So then, okay, I can assembly validate some setup, measure samples, or some configurations that I want to compare with others, and so on. This is the work. I will go into the details of work in the lab later on. Less about simulations, because it's, I mean, it's I would say 20% of my work, and you will probably see much more later on from other seminars. Then we have meetings, and meetings are they are necessary most of the time. A colleague of mine would say that they are a practical alternative to work, which is a very smart way of seeing it. Then publish, of course, the gain that you get, and this is one of the most important things that we do. So publishing and being part of the peer review of papers and so on is really the net which keeps together this scientific society. So it's really important, much more than patenting, of course. And then, okay, you might have to you have to probably at some point of your career to find the money to repeat this process over and over again, and to make it possible for other people below you, other students that would like to find. Okay, then I will give you some examples, specific examples of what I do, and we could we could split them in 3 parts. So it's this is where I started. Basically, I started by characterizing scintillators in general, and then after that, developing some parallel technologies to make them better. So I will start from this, which is at the end market driven, most of it, because it's medical physics and medicines in general. I mean, you want to save people, yes, but you want to make money as well. Photodetectors as well is partly related to medical physics as well. So this is also partly market driven, but also not, because it's tightly related to a big part of the work that I'm doing, which is not at all market driven, as I will show you. Oh, well, okay, it's not something complicated. CERN is not, in general, CERN is not made to make money or to make products. It's more to get knowledge that we don't have. And this is the last part. So the electromagnetic calorimetry that we are developing for LHCb for the next upgrade, which would take place in 3 years. This is at CERN, and is totally outside of the definitions that we found in the first slide. And of course, these 2 sections are tightly related, because I could not do the job that I do now if I didn't do the one that I did before. So somehow everything comes together thanks to the fact that I had my own process. And the process is what R&D is. It's the way that I will show you how R&D works in general, I think. So I start from scintillator, I said, and this is a brief intro. I don't know if you know what they are, but I guess you have a hint from some of your courses, at least some of you. Scintillators are materials which emit light when they receive energy in form of, okay, it has to be very localized energy, so it cannot be heat. It has to be some particle in general. So when they stop part of the energy incoming from a particle, they respond by emitting some light, and this light is proportional to the amount of energy that is deposited in the crystal. That's the trick. So what you have is an electron which jumps from the valence band to the conduction band, and then it thermalizes inside the conduction band by several processes, scattering, Compton, and so on. Oh, sorry, Compton, Rayleigh. No. Sorry. Well, okay, just thermal process, let's say, and then at some point phonons as well. Whenever you find a conduction band that you can follow, and when you reach the bottom of the conduction band, you can recombine with a hole in the valence band by emitting one photon, which is the process of scintillation. And the number of these photons, as I said, is proportional in principle, if you have a good scintillator, to the amount of energy that you deposited at the beginning. So specific R&D objectives could be increase the amount of light emitted, because the more photons you have, the more the statistics, the more precisely you can define what's the energy and maybe the time as well of arrival of the particle. Shorten the decay time because of pile-up problems. I don't know if you know what pile-up is, but the shorter the signal, the more signals you can have one after the other without them to be screwed up by the fact that there was another one before it. So it's not sitting on the signal before. And increase the density because you want to increase the sensitivity, and this is a major problem in medical physics, for instance, but as well in calorimetry. So scintillators are used in calorimetry as well, and you will see them later on in the presentation. So one specific example of what I had to do at the beginning was to answer a question. Usually you find yourself in a group and you start your career. They ask, how can we simulate correctly the scintillators? And okay, then somehow you have to find your own setup. Of course, you have a tool, which is Gen 4 in general, but you can have others. For me, it was Gen 4. You have to find the crystals, which can be in the lab, or you have to buy them. And then you have to put together a method to somehow measure it, because before to simulate, you have to understand what you have in the hands. So you have to first characterize, then you want to simulate what you characterize, and then maybe you can extrapolate from this simulation to obtain something which is not related to what you are doing in the lab. So in this case, was okay. You have to put a photodetector on the scintillator. You have to have some optical coupling between the photodetector and the scintillator. Otherwise, you don't extract all the light, because you have reflections at the surfaces with the PMT. So you want to match the refractive index of the crystal. Okay. From the crystal to the PMT, which is glass, you're going from, I don't know, let's say 1.5 refractive index to 1.5. You go through air, then you have a lot of total internal reflection because of because of Schneer's law. I don't know if you need some optics, but okay, it's the same thing. Why you look at the surface from the surface of the sea from underneath the sea, you cannot always see the top because somehow light is trapped inside. Okay, then once you get your crystal and you nicely set it up, you put some wrapping around it because you don't want to lose the light which is not going towards the photodetector, so you want to redirect the light which is everywhere else towards the photodetector, and somehow you try to optimize from a classical way the amount of light which you are extracting from the scintillator. So at the end, by doing it, you obtain a spectrum of energy. If you measure the PMT that you have attached, or the photodetector that you placed on the scintillator, and you make analysis out of it, which at the end is just a spectrum of the integral of the pulses that you obtained. And you will see after performing this process a spectrum which is similar to the one that you have here in the screen, where you have a Compton shoulder, you have a photopeak clear signature from the source that you are using. So in this case, ionizing radiation was a 511 keV photon. And this is widely used for medical physics setups. So whenever you have a radio tracer inside the body of a patient, usually it decays by beta plus, which is an emission of a positron, and then this interacts with electrons and they emit a photon back to back. And with this, you can track really where the generation took place. And the radio tracer is made to go in the cancer, so you can, by making many of these lines, you can track it. You can see where it is. And okay, so you have the crystal. You made it at the best of your knowledge. You measured it, and somehow you want to see how this can be simulated. And okay, in that case, the trick was to have several lengths of this crystal. So it was an LY, this is the name of the crystal. It's a type of crystal that is widely used in medical physics. And it was a 3 by 3 millimeter by a certain length. And we had several lengths. And the trick there was really to try to match simulations with all these lengths so that we had more leverage on the parameters that we had in the simulation. So I had many crystals, I characterized them all, I put them in the simulation, and then I nicely matched with this parameter, which is sigma alpha, which you don't know what it is, but it doesn't matter. I matched by changing this parameter the measurement with the simulation, and then I had my nice tool which I could use to do other studies, which could explore a wider spectrum of parameters. Okay, yes, sigma alpha, very important. That was the target of that study. It took a while, and it was very interesting. And of course, along I had to develop a method, which is once again, it has to be systematic. Okay, example number 2, I went on in my research, and somehow we wanted to make scintillators even better, and we wanted to fight this total internal reflection, which if you are using an optical coupling, it's always there anyway, because the crystal that you're using has a refractive index which is so high that there is no optical coupling that can match what you have with the crystal. So somehow you always have losses. In any case, even if you find an optical coupling, also the PMTs are made of glass, so you will find another problem just at the step above. So question once again, can we increase the light collected at the photodetector side by not using classical methods, which are easy to do, but they have a limitation? And the answer in that case was to use photonic crystals, which are very tiny structures that we printed to the surface of the scintillator of this kind, like cylinders, small cylinders, and these are on the order of this P. The distance from these pillars could be minimum 300 nanometer, but it could go up to micron level, some microns. And by placing this on top of the scintillator, it was not me. So the idea was not mine. I found somebody else's work. I somehow I catched up with it, and from that point I could start to develop my own method. So the idea was already there. That's another example of R&D, because if somebody else asks you a question, the first thing that you do is not that you start from scratch, but you look for somebody else's work. That's the strength of the common knowledge that we had that we have, as I said, it's the publication list that you have, and there are tools like Google Scholar that you can use to search for publications, and then you start from the basis of other people. We are sitting on the shoulders of giants. Something that you always heard, and this is very true also in this case. So I found somebody else's work, I put it together, I tried to emulate as much as possible, and then from that point on, I developed my own method, which was specific to the case that I had in the lab. So once again, I had some LYSO crystals like the one I had before. I put together my own simulation that together with Jan4, which is just a ray tracer, a Monte Carlo simulator, was working along it to try to cope with the fact that Jan4 is not able to do photonic simulation, so it's not wave-like, it's just particle-like. So I had to merge these two code together, and then use it to understand what was the best configuration possible for that specific crystal, which I had characterized very well just before. So I used my own work as well, my own experience. Okay, and then thanks to the fact that we have this grating, that this net of pillars, what is happening is that you don't have only the main reflection, but you have several orders which are taking place as well, which they have some probability of taking place. They of course don't. At the end, is only some of these orders will be visible, but in the case of this specific structure that you see here in yellow, we had a very nice confirmation of it. The efficiency that we could obtain was higher than the classical way, so that was one of these exciting moments that you can have in your R&D along your career. So a confirmation of after all the work of the simulation, characterization, and so on, you start to extrapolate from this knowledge, and you really pinpoint something new, which is not something that was known before, and it's very exciting. So this is an example of what you see here. These orders that are showing up in red and purple are the secondary orders, first order and second order, not the main one, which is the big arrow here. And these are the ones that we see here as well. We have a laser which is incoming from the back perpendicularly, and we have the main order, which is here in the center, and then we have several of them around, and not only the first and the second, but many of them, just because whatever we placed on top of this crystal was not as perfect as it was in the simulations, but yet we could predict exactly where this point should be, and we had a nice confirmation of the fact that not only we had a gain from the extraction of the light from the crystal, but the gain was coming exactly from where we were expecting it to come. So instead of Snell's law, at this point we had a more complicated law, which includes these orders, and we also mathematically encapsulated this success to publish it at the end, because that was also the purpose. There was also a market-driven purpose at that point, because as I said, this was for medical physics, so there was some interest from some company to try to obtain this. But nevertheless, we managed to publish it as well, which is what was my main concern. Example number 3 is not really an example similar to the other two, because it's more like giving you a feeling of the fact that somehow R&D for us nowadays in Italy or in Europe in general is more like, since it's going towards as well what is called blue sky research in many cases also, but in general also R&D and E, which is very close to industry, is somehow getting money from public money in Europe, and you have to find. You will have several courses, probably optional, maybe, I don't know, but there will be ways for you to understand how this European funding works, and it's very important for you not to do that from the very beginning. At the beginning of the career, you don't do it, but keeping in mind the fact that there are some schemes that are working in a certain way is very useful for your work, because at some point you might have to do it, and if you already know what is there, whenever it comes the possibility to do it, something will trigger in your mind, and you will say, okay, maybe we can do something through a certain financing channel, and this is very important, I think. And this is why usually, at least I did when I was your age, there was some possibility of getting some courses on this stuff, and it's very important. I could get my own project when I was during my first postdoc, and I got it. It was a very good chance, and but I was keeping an eye on this kind of stuff, and I think it's tightly it's there, and it has to be used because it's a very powerful tool. Okay, and I have a couple of examples of what I did with that. We developed some photo detector that were somehow targeting very good performances that cannot be reached nowadays, and we obtained some good results. But at the end, okay, we stopped it because it was not there was not enough profit at the end, because that was money driven. Okay, and then another example that you should probably keep in mind is the fact that sometimes in R&D you will find yourself probably at the beginning, especially to do some very a lot of characterization and boring work, but this is part of the game, because I mean it can be boring, but it helps to develop. Well, you get some knowledge, hopefully, and not only doing boring work all the day long, but you also get some knowledge, and it helps to develop your own method, which is going towards the fact that you have to learn to be systematic, as I said before. So, and the method comes with doing it. It's like studying. At the beginning, you don't know how to do it, and you screw up, but after a while, you get along and you understand how to do it, and you perform better also in exams. It's not that you are that much different from what you were before. It's just you develop the method, and this helps a lot. And okay, so in general, all these three examples, they, as I also introduced before, they put together some basic knowledge that I carry with me. Is my bag of experiences, and this allowed me to somehow enter bigger collaborations and a wider idea of R&D. Again, we go from market driven to something wider, something that we want to just know what is not known. We want to explore. And this for me was CERN. So during my master, I started already at CERN with the characterization and so on, but I was there since the master thesis. And okay, this is LHC. You know it, I guess. And I was sitting here. I'm still sitting there. And this is the place where I work now. This is the collision point number 8, and this is where LHCb is sitting. This is one of the big experiments that are sitting at CERN. There are many, big, small. The well-known one are CMS, Atlas, LHCb, Alice, but there are also satellite work that, well, yes, some experiments that do. They are smaller. They are not as expensive, but they also do nice stuff. Okay, I'm working in LHCb right now, so that's my main task. And specifically, I work on the calorimeter, which is this yellow part here, the electromagnetic calorimeter. There are two calorimeters usually in the experiments. One is for hadrons, and one is for electrons and photons. I work on electrons and photons. Okay, so specific examples. Once again, we go into the details of what I do. And this is the upgrade plan. I mean, I will show you the upgrade plan of the LHCb ECAL. So, and I start from what we have right now, because otherwise you don't understand. So right now we have a wall, which is this yellow. I mean, the yellow here you see on the side, we're just seeing a front view of it that we had when the calorimeter was open. The good thing about LHCb is that there is a lot of space, so you can open it and you can see it and you can work on it. It's a big advantage. Okay, it's optimized for pi 0 and gamma identification from few GeV to 100 GeV with a certain luminosity. It uses right now, so the current configuration uses Shashlik technology, which has some scintillating fibers running through a stack of scintillators and absorber. We need the absorber because we have to make this module dense. And okay, we have a certain number of them, 3,000, and this makes up for a 50 square meter wall, which is pretty big. We have different type of modules, but this is not very much interesting. Okay, and the upgrade has to cope with the fact that somehow there will be much more radiation during run 4 and run 5, which will start in 3-4 years from now. 4, yes. So somehow we have to develop new technology because the current Shashlik technology cannot cope with that. So the fact that we have much more radiation means that the materials will be damaged much more easily, and we have to develop a new technology which doesn't use these scintillating fibers which Shashlik is using, which is WLS, wavelength shifting fibers, but fine. We have to find something new. And this new thing is what I'm showing you here. So instead of having scintillators running through a stack of absorbers and scintillators, once again, we have scintillators, which are the yellow one, which are put into the holes of modules which can host these fibers, these scintillating fibers. This is different because the scintillator that we can put can be radiation hard, while the fibers, I think I put another picture here, the fibers that are running through this stack, they have to be WLS, they have to wavelength shift the light which is emitted by the light blue part here, because otherwise they cannot, the light which is emitted in this layer cannot be transported to the PMT, so they have to re-emit their own light, and then this light can be transported in this fiber. In this case, the light which is emitted in the yellow part is already transported to the PMT, and the technology for producing scintillators, which are already radiation hard, exists. So that's the difference between the two technologies. Okay, and then we are planning to have different regions depending on the occupancy and also on the radiation damage. We have some simulation tool that tells us how much radiation we will have in a certain region of the wall and how much particles we will have per second, let's say, so the occupancy. And like this, we can determine how finely we have to look at specific regions. So in this red part, which is close to the center of the wall, you see the beam pipe is here. The interaction point is along the axis which is going through 0, 0. These modules in red are the ones that will see most of the things, and so we have to make them smaller in the readout side. And we also have to make them much more radiation hard, because seeing more things means that they also suffer much more radiation. So somehow we have to have different technologies for different regions. And okay, I'll go through it. This is just the planning, but not very interesting. And this is the occupancy that I was talking about. So this plot tells us how many particles we have per bunch crossing. So every time that the two bunches collide, we know how many particles we will have in each specific pixel of this map, which is a specific channel of the equal of the calorimeter wall that we are reading. And on the left, you see before the upgrade, and on the right, you see after the upgrade, in the condition that we will have in a few years from now. So you see the difference between the two. And this is one of the things that I had to follow closely, because since I'm developing the technology for the modules, so I'm developing the new scintillators with the absorber and so on. I'm the one who is developing. I'm helping in developing it. It's not a work that somebody can carry on by himself. So it's a group work. But that's the part of the work that I'm mostly involved in. And I have to be tightly involved with the simulation, because of course these two things has to talk to each other. You have to know how it will behave when you place it there, and otherwise you're blind. And this is what they did basically 20 years. And they were not blind, but the simulation tool that they had, it's quite astonishing how they managed to do what they did without that, without the technologies that we have nowadays. So we are lucky to have the level of details that we can reach today, and we have to use it. And this is what I'm doing by looking at these simulations and sometimes also running them. So this is an example of differences in the signal to noise ratio that we can obtain, once again, in the simulation, in the condition that we will find in a few years from now with the current technology, black curve, and with the upgraded technology that we are proposing, and that's the red curve. This is one of the plots that we used to justify the fact that we wanted money for the upgrade. I mean, nobody will finance the fact that you want to upgrade the calorimeter if you don't demonstrate that there will be a gain. So this is the tools that we are using with the financing section of our experiments to ask for money. And I went. Okay, and then this is an example of how specifically shashlik is made from the readout point of view, which is of some interest. There are some numbers as well of the kind of energy resolution that we can reach with these modules. You didn't have a calorimeter course, I guess, yet, or any kind of high energy physics course, but usually energy resolution for high energy physics is defined with several terms, two of, well, there is noise, and then there is sampling term and constant term, and usually we use these two numbers to quantify how good they are in saying what's the energy of the particle which they stop. This is one of the things, and then we have the time resolution, which is also very important. So we have also to be able to say when the particle reached the calorimeter level, because it helps in the analysis of the full processes at the end. So these are the numbers for shashlik. Okay, we have to demonstrate somehow that with the new technology that we are proposing for shashlik, because we are also producing some new shashliks that could live in the outer region of the calorimeter, as well as for the new technology that we are proposing, which is spacal, as I said. So these are the fibers that that runs through directly to the PMT. Okay. Okay, so as I said, we have to keep more or less the same numbers that we have for shashlik, but we have to be radiation hard, and we have to be able to maybe determine the arrival of the particle, the arrival time of the particle with a better time resolution. And this is what I helped in building. It's a spacal module that we measured 2 years ago during COVID in DAISY and SPS, which are two facilities that allows us to characterize the samples before we put them on the wall, because of course we simulate, we build, maybe we resimulate the thing that didn't go very well, and then we have to somehow characterize what we have, and we take it, we bring it somewhere that can give us electrons with high energy, and this is possible in SPS. We also need low energies, which SPS, which is at CERN, cannot give. So we go to Hamburg in Germany to characterize at low energies. And this is also part of my R&D. So traveling around to characterize stuff is part of the work. And it's fun. Okay, the PMT that we used is this one. PMTs, I was lucky to have the experience that I had before because I knew them very well. And nowadays I'm learning even more because there are people that are much more expert than me, including Angel. So yes, so this is one of the prototypes that we built, and how it behaved is shown here in these two pictures. I don't know if you're interested, but we could reach 20 picosecond time resolution at 20 GeV electrons. With the other technology, we are able to do 40. So we brought down a factor 2 in time resolution. We being able to also do it with radiation hard technology, very important. And energy resolution was at the level of the technology which is already there, which is shashlik, and it's already very good. So the requirement there was to keep the same resolution, and we managed to do that. This is another prototype that we made. You see here these little yellow squares. These are the fibers that are facing on this side of the module. And here we have the readout, which it was removed, but there we have light guides and PMTs, which collects the light and bring it to the PMT. This is another technology. It's even more radiation hard. So this is the technology that has to go in the very center of the calorimeter. This can go up to 1 megagray, which is huge. It's very high. It's very expensive. This module was very expensive because these tiny crystals they are crazy to make. They are 5 or 4 centimeter long in this section and 10 centimeter long in the other section. So it's a completely different R&D and parallel to develop these kind of things. And then they come out expensive, but hopefully with large scale production we can bring it down. Fine, so slightly different geometry is also something that I helped in developing, and this was fully characterized in both DAISY in Hamburg and SPS as well, which I don't have the plot here, but it was good anyway. So we we managed to reach the target also with this technology. And this is the very first prototype that we made just 1 year ago, or even less, which has the full size of the module. So all the one that we had before, they were smaller. They were not the full size 12 by 12 centimeters of size. Somehow you have to cope with the fact that you have to build a wall with bricks, and these bricks have to be 12 by 12 centimeters. It is a requirement that comes historically from the experiment. So yes, okay, we somehow started from small prototypes, and we arrived at something which is more and more similar to the shape that we finally have to have in a couple of years from now, because in a couple of years we will have to start to produce 30 of this kind. We have to produce 144, and of the other kind we have to produce 32. So the closer we are to the final configuration, the lower the probability that we are messing up, basically. So we are starting to do as much as possible, because you never know what can be. I mean, scaling up the technology might seem easy, but at the end is not. For instance, this module, curiosity is the fact that somehow you have to keep it together. Here we are keeping it together with an outside mechanics. You see, these aluminum pieces are just meant to keep together all these fibers and this heavy material. But somehow in the final configuration you cannot have it, because you cannot have that material in a calorimeter. Otherwise you will have losses, and you will have a deterioration of the energy resolution. So somehow this cannot be there, and we have to somehow invent some new ways of keeping everything together with just one tiny small screw, as tiny as possible, to avoid having losses once again. And okay, it's just something that complicates everything in a way that it's not even imaginable, but we will make it somehow. And so this is the process that we are doing right now. So now I'm here, but somebody else is working for me at CERN to try to understand how to mechanically keep everything together also without this outside aluminum frame. And okay, once again, we could obtain the performance that we had as a target, and this is by now not a problem for us anymore. It's more a problem of scaling up for other part of the detectors, like the electronics, or the fact that the PMT that we are using right now might be too expensive. So somehow we have to scale down and compromise and discuss with the producer. This is all part of R&D. And this is a beautiful and complex system, which is very challenging, all the time different, and I love it. And this is just some details of how this is made, and then I'm done. So I think I'm it is made of 3D printed tungsten, which is very dense, and these holes are the one that we insert the square scintillators. And there are several pieces which are kept together by aluminum. This is the aluminum frame that you were seeing before as well. And inside this square, we inserted the scintillators that you saw in the picture before. And here on the left, you see the module in the box with some PMTs. And inside this black part here, we have some light guides, which we developed our own, because we had somehow to have light guides which are radiation hard, and usually light guides are made of PMMA, plastic. Plastic is not radiation hard at all. So we had to make them somehow hollow with this reflector, which is glued on a 3D printed piece. We 3D print, we developed our own idea of light guides, we glue them, we find a way to cut them. We did the R&D of this module. Basically, we did everything in-house, more or less, apart from the printing process itself, which is taking place outside because the machines are crazy expensive. But for the rest, is everything done by our own hands. These are the PMTs that we used. Now we're using different ones because these are too expensive. Yes, this is what the yellow box is saying. And then we had to have some calibration light on the other side as well. So we had to do it as well. We had to do the cables. We have to find connectors, find the best way to connect it to the module, insert the connectors in the module. This was a tedious work, but at the end it was quite nice.